Hi, good evening, everyone. Can anyone please confirm if you are able to hear me and are able to see my screen?
Yeah, you are audible.
Yeah, and is my screen visible?
Yes, yes.
Yeah, thanks a lot. Okay, so good evening once again. I am Nand Kishore. I am a PhD research student in the Department of Electrical Engineering, IIT Delhi. So I am one of the teaching assistants for this course on fundamentals of power electronics by Professor Homanand. So we will jump right ahead into the problems. I assume you guys would have gone through the lecture slides corresponding to week one. So basically, you guys studied about different switch characteristics and the characteristics are um, that are there for an ideal switch, but of course you don't get that practically. And in this week, you focused a lot on diodes. That is, you studied the static VI characteristics and came into the dynamic aspects of the diode characteristics pertaining to the diode reverse recovery and calculation about its reverse recovery time and losses and the TRR, QRR aspects of that. Following that, you came into how to estimate the power loss in a diode, right? That is, you know that the diode has a specific cut-in voltage, and of course, a practical diode would have definite RD, that is the resistance. So corresponding to that, you of course have some power losses, and you came into how to calculate those power losses. And based on the power loss, we generally determine what is the thermal aspect, right? That is based on the TJ that you require, that is the junction temperature. You determine what is the heat sink that you require, the R theta or the thermal resistance of the heat sink required and stuff. So we will also be going through problems on how to calculate the power losses and how to um, how to select a suitable heatsink based on the maximum temperature that's allowable, right? So problem solving session would be mostly oriented towards that. And apart from that, you of course had lectures on KiCad, that is how to design the schematic and stuff. Of course, there is no problems oriented towards it, so that would not be covered in today's session, right? So today's session is mostly towards problem solving. I'm having some throat infection and cough issues, so if in case my voice is not audible, please do let me know. I will try to repeat it once again. Yeah. Yeah, so before we move ahead, um, how we define an ideal switch, you can come out to the last row in this table. That is, an ideal switch is supposed to be fully bidirectional in terms that it can block bidirectional voltage and it can conduct current in both directions. And of course, it needs to be completely controllable, right? So it can control by it can block voltage, positive voltage, negative voltage, and it can conduct current from anode to cathode or cathode to anode, right? So that is what is the definition of an ideal switch. But of course, you don't have ideal switches as such. You might, of course, know that there is one way of realizing. I mean, there are multiple ways of realizing fully bidirectional devices. We will be seeing that in the course of the weekly problems as well. One of the examples is this triac that's shown over here, right? It can, of course, block bidirectional voltage and conduct current in both directions. So in this particular week, we will be seeing problems on this, right? That is diode. You of course know that diode is an uncontrolled device, right? So it's an uncontrolled device in the sense that it is able to block negative voltage, right? That is from cathode to anode, and it can conduct current only from anode to cathode, right? So it's an unidirectional device and blocks in the opposite direction, and it is of course uncontrolled. If you want control, you of course need to go towards BJTs or GTOs, FETs, SCRs, right? SCR, DAC, track, and stuff, right? Okay, so we will jump right into the problems. Initially, the problems are a bit simpler, but anyway. So the first problem is unit of thermal resistance is dash. Okay, So you might of course know that thermal resistance is actually R theta, right? People write it this way, or people can also write it as RTH. So whatever is your wish. However, you can understand that from this very basic definition, resistance is basically what in electrical terms, that is V by I, right? This is electrically, right? But thermally, we define thermal resistance as some degree centigrade per watt. Okay, that is the analogous representation in the thermal domain is something like this. So just hang on a second. Yeah. So generally what we do is, for example, let's consider a simple circuit, right? So you have a voltage source and you have a voltage source, right? And a load resistance, right? Let me call that as RL. Okay. So due to this connection, there would be a current flowing in the circuit, and let us denote that as I. So we of course know that I is equal to V by RL. So this is in electrical terms. Okay. However, if you do the same thing thermally, then what you end up with is something like this. So you have an R theta, okay, and I will have a current source, right? Okay. So I can write this as P loss. Okay. So this is the current that's going into the circuit or that's flowing in the circuit. How is it flowing? Why is it flowing? We'll just come to that. So um, let me erase this stuff off. So why will this current flow or why will the P loss flow? It's because you have a temperature gradient or you have some amount of T over here. Okay. So a temperature, um, when would temperature increase, right? Or when you say that you have some equilibrium temperature, what does it indicate? It means that there is a specific power loss happening across this resistor, and corresponding to that, we have some temperature across this resistor. Okay, so if the power loss is more, then you obviously know that the temperature is also going to be more. So the analogous fashion would be something like T is analogous to voltage, and the P loss is analogous to current, and of course the R theta is analogous to your load resistance. Okay, so coming back to our point earlier, the unit of R theta would obviously be what? The unit of R theta would be obviously, let me just add a new slide. Yeah, so the unit of R theta would be temperature divided by power loss, right? Temperature divided by the power loss. That is why I had written it at degree centigrade per watt. Okay, so this is the unit of R theta or the thermal resistance. So in the above example, nothing is given in terms of degree per watt. So we just need to figure out what that is. Okay, so here most of the examples are in terms of Kelvin. That's of course analogous to degrees, no doubt regarding that. But over here they have given it in terms of joules, right? So what is joule? Joule is something like watt into second, right? That is the power into time equals the energy. Okay, so watt can be written as joule per second. Therefore, unit of R theta is going to be degree centigrade per watt is joule per second. Okay, or Kelvin per joule per second. Okay, right? So if you have any doubt, please do ask now. So you can understand that the answer is going to be C. Kelvin per joule per second. Okay. Okay. So unit of R theta is degree per watt or temperature per power loss. That's the easiest way to remember. Let's go ahead to the next one, right? So this is a simple theoretical question. As compared to PN junction diodes, that's the normal yeah. As compared to the PN junction diodes, the Schottky diodes have dash. Okay. So this is your PN junction diode, and then you have the diodes have dash, right? Low operating frequency, low reverse leakage current. High operating frequency, low reverse leakage current. Medium operating frequency, low reverse leakage current, and high operating frequency, high reverse leakage current. So what happens in a Schottky diode is, instead of the conventional PN junction that you get in a normal diode, right? You have the P layer and the N layer, and of course the uh, barrier. Instead of that, in a Schottky diode, you replace one of these junctions with a metal contact. Okay, so you do have a P region and then a metal contact. Okay. So what advantage this gives is that the reverse recovery current is going to be lesser for your Schottky diodes. Okay, that means that the TRR, right? TRR of these diodes, of Schottky diodes, are going to be way lesser. If your TRR is lesser, it means that your turn off time of the diode is going to be lesser. Okay, since your turn off time is going to be lesser, it means that you can turn on and turn off the diodes even faster. That is, let's say this PN junction diode takes 10 microseconds to turn off, right? Including the reverse recovery time. The Schottky diodes are going to take much lesser, right? It can be even an order lesser, right? In that case, the T off is going to be lesser. Therefore, you can use these kind of diodes, these kind of diodes for high frequency applications. Okay, that is, you know that if your frequency is high, your entire on period is or the on duration itself is going to be lesser. Therefore, you require fast switching times. Okay, fast switching times, and these can be provided by Schottky diodes. Why? Because they have a metallic contact, the reverse recovery is not there, right? Therefore, you can use them for high operating frequencies, and but the drawback you get is with Schottky diodes, you have a high reverse leakage current, and that is mostly attributed to the presence of this metallic contact. Okay, right. Okay, so one of the differences between diode and triac is dash. Diode has controlled. Okay, so before we even go to the problems, diode is totally uncontrolled, right? And unidirectional. Whereas triac, as you might know, it is an anti-parallel connection of two ACRs, right? So you have something like this. Okay. So what you can get is you can have current flow in this direction with this ACR, you can have current flow in this direction with this ACR, and of course you can block positive voltage as well as negative voltage. Okay, so positive voltage blocking is there, negative voltage blocking is there, and of course bidirectional current conduction is there, and it is completely controlled. Okay, so this is it is totally controlled. Okay. So from this itself, you can figure out that the option is going to be D. That is, diode has unidirectional current flow, triac has bidirectional current flow. Okay, it's a very simple theoretical question. Okay. So the next question is features of an ideal device. On resistance is 0, off resistance is infinity, during on condition. Sorry. Yeah. So during on condition, conducts infinite current in both the forward and reverse directions. During off condition, which sends infinite forward and reverse voltage, all of the above. So I guess you have realized that all of these options are true, right? That is, on resistance, of course, is 0. Power loss. Okay. Yeah. Okay, so it means that there is going to be no power loss, and during on condition conducts infinite current in both the forward and reverse directions. That is plus and minus I is possible. During off condition withstands infinite forward and reverse voltage, plus and minus V is possible. So the correct answers, as you would have guessed this, all of the above. All of these are the characteristics of an ideal switch. But of course, you never get that with practical switches, right? Okay, right. So a transistor is connected uh, in parallel with a diode in reverse mode. It has a capacity of dash. Okay. So you have a transistor. Let's say that's a MOSFET. Okay. So it inherently has a body diode. They have not specified about that, so we will see, right, whether it fits into one of the options or not. Okay, a transistor is connected in, because they haven't mentioned what kind of a transistor this is. It can be MOSFET or BJT as well, right? So it is connected in parallel with a diode in reverse mode. So it is connected with the diode in reverse mode, right? So you know that for a MOSFET, this is your drain, this is your source, and this is your gate, right? So this is your drain. So this is your drain, this is your gate, and this is your source. And a diode is in reverse mode, right? So obviously this is your anode and this is your cathode, right? So it has the capacity of dash. So you just think about it. Obviously, it can conduct current from source to drain, right? So negative current conduction is possible. Negative I is possible.
Hello, Kishore, are you sharing your screen?
Sorry,
Are you sharing your screen? You're not able to see your screen.
I'm sharing my screen. Is anyone else not able to see? Or for me, it says it is sharing a screen and audio.
But I don't see
Yes,
your
sir, it is
screen.
visible.
Okay, it's visible, right? Okay, so what you can do is you can log out once and log in again. I think then the issue would be fine. Okay. Yeah. Okay. So the question is, are transistors okay? So it can obviously conduct from source to drain because of this diode, right? So negative current conduction is possible. Then what else? Can it block voltage from source to drain? It cannot block voltage from source to drain because this diode cannot block voltage, right, from anode to cathode. So negative voltage is not possible, right? Negative current is possible. So what about drain to source? It can conduct current from drain to source, right? When I give gate pulses to this MOSFET, it can conduct from drain to source. So positive current is possible. So first of all, I forgot to define. I am taking this as the positive terminal, okay, and this source as the negative terminal. So positive current means plus to minus, right? And positive voltage blocking means across plus and minus, okay. Okay. So it can conduct positive current from drain to source when you give gate pulses, and when you withdraw the gate pulses, it can block positive voltage from drain to source. Okay. So we have got operation in three quadrants, right? So if you guys are familiar with the quadrants of operation of a device, you would understand that you have something like this, right? That is, this is plus V, minus V, plus I, and then minus I. So what all are possible? So what all are possible? You have negative current, right? You have positive current, you have positive voltage, right? So in this entire quadrant 1 and quadrant 4, the device can operate, right? You can have operating points in this region. Okay. And of course, negative voltage is not possible. So coming back to the question, it has the capacity of what? It has capacity of bidirectional current conduction and unidirectional voltage blocking, right? So bidirectional current carrying capacity and forward voltage blocking capacity, right? Okay. Okay. So another simple question: which of the following has bipolar voltage withstand capacity? SCR, GTO, SCR and GTO both, none of these. So you can understand that. Let's take the case of an SCR, right? So you have your anode, you have your um, you have your um, anode, you have your cathode, and of course you feed an IG, right? Gate current is required to be fed. So you can understand that it can of course block VAK, right? VAK it can block, right? And when you give a gate current, right? When you give a gate current more than your latching current of the CR, you know that it can conduct current from anode to cathode. Okay, IAK is also possible. However, IKA is not possible, right? Why? Because it's like a diode, right? So it can conduct current only from anode to cathode. The reverse is not possible, right? Unless you have some other arrangement. So IKA is not possible. And can it block VKA? Yes, it can block VKA. Why? Because again go back to the reference of a diode, right? Because you can block voltage between cathode to anode, but not between anode to cathode. Here we see that it can block voltage between anode to cathode, provided you don't give any gate current, right? So coming back to the quadrants of operation, you can understand that for an SCR, this is plus V, minus V, plus I, and then um, this is your minus I, right? So where can it operate? Um, so it can block positive voltage, it can block negative voltage, and it can conduct positive current. Okay, and that is between quadrants 1 and 2 it can operate. Okay, so it has bipolar voltage withstand capacity. That's the case over here. Similarly for GTO as well, right? GTO is actually a gate turn off transistor. Why were GTOs invented? Basically because if you go through the um, properties of an SCR, you would understand that SCR has controlled turn on, but turn off is not controlled. Okay? Uncontrolled, or people call it semi-controlled as well. So uncontrolled turn off. Okay. In order to overcome this particular drawback, we went with what are known as GTOs. GTOs were invented. That is wherein you try to use this gate again to control its turn off as well. So you can understand, you can understand that in an SCR, once the SCR is turned on, right, even if you remove the IG, right, even if you remove IG, the SCR can remain in off on condition. Okay. This is one of the drawbacks of an SCR. In order to turn off SCR, there is a separate turn off mechanism for SCRs, and there are commutation circuits as well. So in order to turn off the SCR, you need to first apply a huge reverse voltage across the SCR, and of course, make sure that your current goes below your holding current. Okay, IH we call it. So this is kind of a tedious process, and that's why we call the turn off to be semi-controlled or uncontrolled. So is it possible to actually use this IG itself, that is the gate current itself, to turn off the device? The answer is yes, and it is possible with GTOs. However, pertaining to this question, GTOs and SCRs are similar in terms of their bipolar voltage resistance capability. Therefore, both SCR and GTO can block both positive and negative voltages. Okay. Okay. What's the relation between the breakdown voltage and drift region of a power diode? Okay. So let's take the example of a PN junction diode, right? So you have the P region and then you have the N region, right? So this can be a normal signal level diode, right? Signal level diode as in like it may be rated for 5 volts or 12 volts or something like that, right? How do you use device same power diodes, that is the same diodes for power applications? That is, let's say you want the diode to block at 1200 volts. You want the diode to block 600 volts, 400 volts. Can you use the signal level diode? Obviously, you can't use. So, what's the addition that you do to make it a power diode? How do you convert a signal level diode to a power diode? The answer is what materials people do is that they add what is known as a drift region in between, right? So what is done is you have the same diode, you have the P plus region, that is P plus indicates that the region is heavily doped with P, and then you have a lightly doped region in between, and then you have a heavily doped N region. Okay, so plus means heavily doped and minus means lightly doped. Okay, so this region over here or this particular area is what is known as the drift region. Okay, so this is known as the drift region. That is, this particular region actually gives it the voltage blocking capability for the diode. Okay, these are the conventional P and N regions that you have in a normal signal level diode, but what gives it the voltage blocking capability is actually this drift region. And it turns out that the width of that drift region, right? That is, let me call it WD, width of the drift region. Width of drift region. Width of the drift region dictates your voltage blocking capability, right? That is, if you have a larger WD, you're going to get a larger voltage blocking capability. Okay, so you can understand that let's say there are two diodes. One is having a voltage blocking capability of 200 volts. The other one is having a voltage blocking capability of 40 volts. The other one is 1200 volts. You can understand that the width of the drift region in 1200 volts device is going to be much larger than 200 volts and then 40 volts, right? 1200 more than 200 more than 40. So the relationship between breakdown voltage and drift region is directly proportional. Okay, as your width of the drift region increases, the voltage blocking capability increases. So you may ask that, okay, why not use diodes with high voltage blocking capability for all applications, right? That is, let's say I have an application requiring 300 volts. Generally, people use devices that are rated for perhaps 450 or 500 volts, right? Why not use a 1200 volts diode for a 300 volts application? It turns out that as WD increases, right, power loss also increases. Okay, this is because as WD increases, your voltage drop or the forward voltage drop also increases. Therefore, your power loss increases. If your power loss increases, your junction temperature will increase. You would have studied about the thermal aspect, right? In that, you would have uh, understood what is the relationship between your junction temperature and power loss, right? So your junction temperature increases, therefore, heat sink size increases. Heat sink size increases. So it has huge repercussions, right? So as the width of the drift region increases, forward voltage drop increases, power loss increases, therefore the junction temperature increases, heat sink size also increases. That's the reason if someone asks, let's say have a 40 volt application, why not use a diode rated for 1200 volts, right? In that case, you can't use a diode rated for 1200 volts purely for this reason that unnecessarily your power loss is going to increase, efficiency is going to reduce, and your junction temperature increases, heat sink increases, unnecessary complications, right? And of course, the cost will also be high. Okay, so yeah, this is just an additional point that I thought it would be good for you guys to know. Okay, so as far as the relation is concerned, if your drift region width increases, your voltage blocking capability is also going to increase. Okay. Okay. So fast recovery diodes are used in dash application, and the reverse recovery time of these diodes is dash. So this is a very simple question. From the name itself, you can understand fast recovery means the reverse recovery time is going to be very small, right? So either B or D. And if you tell that your TRR, reverse recovery time, is lesser, it means that your turn off time for the diode is going to be lesser. So the diode can turn off pretty fast, right? That means you can use it for high frequency applications. Okay, so the option is D. Fast recovery diodes are used for high frequency applications, and reverse recovery time of these diodes is very small. Okay. The reverse blocking capability of Schottky diode compared to power diode is dash. Okay. So as I was mentioning earlier, in a power diode, you have something called as the drift region, right? P plus, N minus, and N plus. However, in a Schottky diode, you replace one of these with a metal contact. Okay. The advantage is, of course, that you have little reverse recovery and stuff. But however, the problem is that it cannot block higher voltage. Okay. So the reverse blocking capability of Schottky diode is actually very low compared to power diode. Power diodes can be rated for 1200 volts in market. Even 1700 volts are 1700 volts power diodes are available. Same thing you can't have for Schottky diodes. Okay, you may see them up to maybe around 100 or 200 volts and stuff. Okay, right. Which of the following devices has controlled turn on and uncontrolled turn off? We just mentioned earlier that controlled turn on and uncontrolled turn off is found in SCR, right? Why do we say that? That's because um, let's say this is your anode, this is your cathode, and you have a specific gate current, right? It's a current control current source. Okay, it's a CCCS, current control current source. Why current control current source? You have a gate current, right? You cannot apply a gate voltage, right? You need to push some gate current. So current controlled, and it's a current source. Why? Because it will, yeah. So yeah, so it's a current controlled current source. Now the point is, why do we say that it has controlled turn on and uncontrolled turn off? The reason is that when you have a gate current and ensure that the current is of course greater than your latching current, that the device turns on, right? It can conduct current something like this. IAK will flow. Okay. And even if you remove IG, right? Even if IG is removed, IAK can flow. Okay. So you know that this IG over here is not, oh my god, it got okay. So you know that as I was mentioning, your IG needs to be greater than your latching current, and if this is true, then IAK will flow. Now, if you remove IG, right, even if IG is removed, you will see that IAK can flow. Okay. In order to turn off the device or commutate the SCR, you have separate. Oh my God, it got turned off again. So you have a separate commutation circuitry. So you have a separate commutation circuitry to turn off the SCR. This is one. Second, of course, you would have known that in order to ensure or in order to turn off the device, you need to apply a reverse voltage. Weak Ka should be positive, and of course, you ensure that the current goes below your holding current. Okay, only then the device can turn off. So you understand that the turn off is kind of semi-controlled or uncontrolled. Okay, whereas the turn on is completely controlled with IG. Therefore, SCR is the device that has a controlled turn on and uncontrolled turn off. Okay, fine. So far, so good. Any doubts so far? From this moment on, we will be stepping into numerical problems. Okay, so far we saw a lot of just theoretical examples. From this moment on, we will try to go to numericals. Okay. Just give me a second. I will have a glass of water. Okay. So we will jump right into the numerical problems. Okay. So this question is pretty simple, and I'm sure all of you know. So piecewise linear IV characteristics of a diode is shown in figure. The cut-in voltage of the diode is dash. First, let me check if I have unmuted. Yeah, I'm unmuted. Okay. So from this graph itself, you can understand that the cut-in voltage is equal to cut-in voltage is 0.5 volts, right? So 0.5 volts. It's a very simple question, right? However, there is a continuation to this. referring to this question again, the dynamic resistance is dash RD. What is RD? So simply from this graph itself, you can understand, or even if you don't know what's dynamic resistance, you understand that R is equal to V by I. In this case, it's going to be delta V by delta I, right? That is the slope over here, 1 by slope, right? So what is delta V by delta I? That is, let's take this, let's assume this is a linear line. Then you know that this particular point is 0.8 volt, comma, 0.9 amperes. And this particular point is 0.5 volts, comma, 0 amps, right? So just find out the uh, slope. So it's going to be 0.8 minus 0.5 divided by 0.9, right? So 0.3 by 0.9 or 3 by 9 or 1 by 3. So 0.333. Okay. Any doubt over here? Dynamic resistance is simply the slope, right? Or 1 by slope. Okay. Right. Okay. So I think the answer is going to repeat over here. Right. Yeah. In a GTO, the turn off is dash, whereas in an ACR, the turn off is dash. Okay. So I think we discussed this elaborately. That is in GTO or in ACR. In ACR, the turn off is uncontrolled, right? Whereas in GTO, the turn off is also controlled. Okay. So in GTO, the turn off is controlled. In ACR, the turn off is uncontrolled. Okay. Okay. Fine. A Schottky diode carrying a current of 5 amperes with forward voltage drop of 0.5 volts is used in a power converter. So IF is given. Um, yeah. So IF is given and VF is also given. Okay. If the diode has junction to ambient resistance of R theta, junction to ambient is also given. Okay. And operating at ambient temperature of 40 degree. Calculate the TJ. Okay, accounting only for the conduction losses. Okay. So first understand what's given, right? So VF is 0.5 volts. IF is 5 amperes. Okay. Junction to ambient itself is given totally, right? RJA. Junction to ambient is 40 degree per watt. Okay. And they have given that the TA or the ambient temperature is 40 degrees. Calculate the TJ. So what is TJ? What is TJ, right? That's the question. And calculate the junction temperature accounting for the conduction losses. Okay. So we discussed this earlier as well. How do you relate the thermal aspect with KVL? That is, you have a TJ over here, or okay. So let me go to this picture over here, right? So you have a power loss. You have a power loss component that is going to occur across the diode, right? That is, you know that this is the diode. It's being used in some circuit. Okay, we need not worry about the rest of the circuit. But point is that it has um it has So it has a forward voltage drop Vf and it is conducting a current of If. So you of course know that there is going to be some power loss, right? Because there is a voltage drop and there is a current flowing across the device. So be it any circuit component, if there is a V into I, there is going to be a power loss, right? Power loss is going to be Vf times If. So this power loss will indeed result in an increase in the temperature. That is, there will be a delta T, right? That is, there is this power loss is actually going to cause a temperature rise. How do you relate that with the thermal resistance, right? So the idea is that let me use a new slide. So first of all, you have P is equal to Vf times If, right? So this is one. Secondly, you know that the junction temperature or junction is the point at which all the power loss is actually going to happen, right? So what would be the junction temperature? Junction temperature would be the ambient temperature, that is the surrounding temperature would obviously get added up with what? It would get added up with the power loss, right? Power loss component. So what is the power loss component? P loss into R theta. Okay. And what is your P loss? We know what is the P loss, right? Vf into If. So you will know what is your Tj from this, right? So that's how you are supposed to calculate over here as well. Um, let's just calculate. So what is Vf into If? I into 0.5, right? That is 2.5 watts. So what is Ta? 40 plus P loss is 2.5 multiplied by R theta. What is R theta? R theta is also 40, right? So it turns out that your Tj will shoot up to 140 degrees. Okay. So this is your Tj. You understand that your ambient was only 40 degrees, but just because of your 2.5 watts of power loss across the device, you are going to get a Tj of 140 degrees. Okay. Yeah, we indicated again 140 degrees. Okay. So referring back to the previous question, the junction temperature that we calculated was how much? We computed Tj as 140 degrees. Okay. So it is outside the maximum operating range of the diode. It is given that the diode can withstand only till 120 degrees. Okay. So prolongated or yeah, prolonged overheating of the device will result in device failure. Okay, or it will reduce the lifetime of the diode. So it is outside the maximum operating range. Obviously, you want to control it. Calculate the thermal resistance of the heat sink to ambient required for the junction temperature to operate at 100 degree. Okay, with R theta junction to case 10 degree per watt, R theta case to heat sink 3 degree per watt. Okay, first you understand what's given over here. So this was the TJ that we computed, that is 140 degrees. But what they want is not this. They want TJ to not exceed 100 degree, right? So that we are within a safe limit, right? Of course, if the data sheet mentions that the device can withstand 120 degrees, it doesn't mean that you will operate the device at 120 degrees, right? You of course take some safety factor into account. And here they have told that you want to restrict it to 100 degrees, right? So for that, we take the refuge of a heat sink. Okay. In this problem, we are going to design a heat sink so that your TJ doesn't exceed 100 degrees. Okay. Fine. So generally, if you take a power device, right? So you have junction which will be inside the device. Okay. Junction is something that you cannot see. Okay. What you are actually seeing is the case. So we have the junction, or which refers to the die inside the device, and it is then encased in a casing, and that is what you actually refer to as a device every time, right? So you have the case, and over the case you want to attach a heat sink, right? And the heat sink is in contact with the ambient, right? So you have three stages over here. That is, junction is where the exact thing is happening, right? That is, the power loss is happening, or VF into IF power loss, TJ increase, everything is happening in the junction only. But how do you take out the heat that is generated in the junction? You take it out, it comes to the case, and from the case, you take it out into the heat sink, and finally from heat sink, it goes to the ambient, right? It is dissipated into the ambient. Okay. Here they have given what is the R theta for each of these cases, right? Let me take a different color. Okay, so they have mentioned that R um, junction to case, that is this particular case, is actually 10 degree per watt. Then case to heat sink is what? Case to heat sink is 3 degree per watt. They are asking what should be heat sink to ambient. What should be this? What should be the heat sink to ambient so that your TJ remains 100 degrees? Okay, understood the question? That is, this is given. Case to heat sink is also given. What should be heat sink to ambient so that for the given power loss, my TJ doesn't exceed 100 degree. Okay, so I will take a new slide. Yeah. So you do know that TJ is equal to TA plus power loss into R theta, right? So if you draw the thermal equivalent model, you will know that you have a TJ over here, um, that is a P loss current source, and let me call this as TJ, right? From TJ, from junction, you have junction to case, you have case to heat sink, and you have heat sink to ambient, and finally you have TA over here. Okay, so just apply KVL, right? Simple, right? So TJ is equal to TA plus P loss into R theta, and all of these are directly cascaded, right? So they are in series kind of. So R theta is equal to R theta junction to case plus R theta case to heat sink plus R theta heat sink to ambient. You need to find out what is heat sink to ambient. Simple relation, right? So they have mentioned in the problem to restrict your TJ, right? Restrict your TJ to 100 degree. 100 degree is equal to what is TA? 40 degrees mentioned in the problem plus what is P loss? P loss is something that we computed in the previous problem. What is P loss? P loss is 2.5 watt. Okay. So 2.5 into what is R theta? R theta is just the summation, right? So 10 degree plus 3 degree plus question mark. So it's going to be 10 plus 3 plus R theta HA, right? So from this, just find out what is R theta. R HA is going to be 100 minus 40 is going to be 60 divided by 2.5.
Sir, the screen is not shared.
Oh, is this a problem with for everyone, or is anyone else able to see my screen? Or okay, so let me share it. For how much time you were not able to see my screen?
No, sir, it just disabled just now.
Oh, okay, okay. Now is it fine?
Yes, sir.
Yeah, yeah, thanks. So you were able to follow this particular problem, right? So far? Um, this particular slide, was the screen visible previously or not?
Yes, it was visible.
Yeah, okay, fine. Thanks. Okay. So what is r theta HA? So it turns out that if you calculate 60 by 2.5 minus 13. Yeah. So you should get 11 degree per watt. So if you put a heat sink of 11 degrees per watt, then you will end up with your TJ being 100 degrees at this operating point. And thus your criteria is satisfied. Okay. So you understood the question, right? What should be your heat sink to ambient R theta so that your junction temperature does not exceed 100 degree. So corresponding to that, we have determined what should be your heat sink size. So this is for 100 degree. If you want less than 100 degree, if this is the question, right? If this is the question, less than 100 degree, it means that your R theta should be less than 11 degree per watt. Okay, so that your drop across the heat sink is even lesser. Fine. So your R theta should be less than 11 degree per watt to ensure less than 100 degrees. Fine. Okay. Now, yeah, so the same thing is written over here. Okay, so before we proceed ahead, is till this point, is it fine? Especially the last two questions, both of them were from the thermal aspect, right? That is how to compute the power loss, then compute the junction temperature, and how to design a heat sink. Okay. If you have any doubt, please do go ahead and ask. Till this point, I'll just pause for a moment.
কি ওষুধ দেখিল মিস সাগরিকা Misa, Nityananda. ମୋତେ କି ରିମୁଭ୍ କଲାରେ
ରିପ୍ଲାଏ ଦେଇନଥିବ ଆଉ।
ମୁଁ ରିପ୍ଲାଏ ଦେଇନଥିବ।
ମୁଁ ଜାଣିଛି ସେ ପଚାରିଥିବ କଣ ନା କଣ।
Hi Arjun, if you have any doubt, please do go ahead and tell. Or if you are not able to unmute yourself, you can type in the chat box. Yeah, so the recorded session would be available for to you. All of these sessions are actually uploaded. I mean, we are supposed to upload these in YouTube. Okay. So by today night or probably by tomorrow, you will be able to see all of these sessions. Okay. And this applies for every week. For every week, it would be uploaded in YouTube, and the links will be shared in. I guess you would have seen one of the Excel files wherein the links will be entered for each week. Also, these PPTs will also be shared, annotated ones. They will be put up in a drive, and we will share the access to the drive and also the link. Okay, that link will also be there in that Excel sheet. You can access that. Okay, or in the next session, in the next week, I can share the link for the drive as well. But I think you can also access if you are a student of that, if you're registered in that course. Which Excel sheet? If you go to the website, it is there one problem solving session, and under a headline called problem solving session. In that, you can actually see the this thing. Okay. At the end of the session, probably if we have time, I will show you that. Okay. After 7:45 or so, if we have time, then I can show you. In that only, all of these will be uploaded. I'll be uploading these PPTs tomorrow or day after tomorrow. Yeah, fine. Okay, so we'll go ahead. Yeah, so far, I presume you don't have any doubts, right? Then go ahead with the next problem. From the piecewise model of a diode, we get dynamic resistance of the diode is 50 milliohms and knee voltage is 0.6 volts. So RD is given, BD is given, right? This diode is connected in series with a 40-volt square wave voltage source. Okay, minimum 0 volts, peak 40 volts, and 20 ohm resistance. Forward voltage drop across the diode is dash. Okay, it's a good basic problem. First, understand what's given in the problem. So they have given what is RD 50 milliohms, right? Knee voltage or the curtain voltage is 0.6 volts VD. Okay. So, and what do they do with the diode? They are actually having a voltage source and they are having a diode over here, and then they have a load resistance of 20 ohms. Okay, 20 ohms, and of course there will be a current. Okay, so I will take the use of another slide. Um, yeah, yeah. So, so what you get is, I mean, what you had is something like this, right? And they mentioned that this voltage source V is having a minimum of 0 volts and a maximum of 40. Okay, so it's going to be something like 40, yeah, with a square wave voltage source. Okay, so it's going to be something like this. Okay, so but what is the question? Forward voltage drop across the diode is dash. So what is the voltage drop across the diode? Right? So that's the question. Cross this to this. So first of all, if you see that the knee voltage is 0.6 volts, please do not take 0.6, right? They have also given the dynamic resistance. So across this resistance also there will be some drop, right? That is I into D drop will be there. So you need to take that into account. So obviously, since your knee voltage is 0.6 volts, the total voltage drop will be more than 0.6, right? Because the total voltage drop is going to be 0.6 plus the drop across the resistance. So the option is not B, the option is not C, definitely. Let's calculate. So the voltage drop, or VF as I call it, is going to be VD plus ID RD. So VD is 0.6 volt plus what is RD? RD is 20 milliohms into what is ID? First, we need to compute what is ID, right? So what are they telling? This diode is connected in series with a 40 volt square wave voltage source and 20 ohm resistance. Okay. So when the diode gets forward biased, there is going to be a current over here, right? So you need to find out what is this current and substitute that. Excuse me, can uh, yeah. Hmm. Yeah. So we need to find out what is ID, right? So what is ID? Again, you can apply KVL. So you have a 40 volt source, right? And then there is a VD drop across the diode, right? So what is VD? 0.6. Okay, it is given in the problem, and I is equal to V by I. That is 40 minus 0.6 divided by RL plus RD, right? So it's going to be 39.4 divided by what is RL plus RD? 20 plus what is RD? RD is 50 milliohms. Okay, so it's 50 milliohms. Yeah, so you can calculate what is this ID. ID is going to be 39.4 divided by 20 plus 0.05. So it's around 2 amperes. That is 1.965 amperes. Okay. So substitute that over here. That is VF is going to be 0.6 plus 50 milliohm 0.05 multiplied by 1.965. So it will turn out to be 0.698 volts or 0.7 volts. Okay, so answer is E, 0.7 volts. Did you guys get this question? How did we do? The forward voltage drop across the diode is just cut-in voltage plus I into R drop. Okay, so VD plus ID RD, right? So you know what is VD, you know what is RD. Both of these are mentioned in the problem. You just need to find out what is ID and plug it in over here. So how do you find out ID? ID is just found out by KVL, right? So let me draw this in a better manner for you guys to understand. Um, yeah. So um, you had a voltage source and you have a diode, and this is the RL. Okay, but the point is this diode, when it is turned on, and if it's a practical diode, it can be represented as a voltage source in series with the dynamic resistance, that is RD, and of course the drop due to the cut-in voltage. Okay, therefore this circuit can be modified as voltage, then so this is your 40 volts over here, 40 volts, and this is your VD of 0.6 volts. Okay, and then you have RD 50 milliohm, and then you have RL, that is 20 ohms. From this you can find out what is ID. ID is what? 40 minus 0.6 divided by 50 milli plus 20 ohms, right? So 20.05. So it turned out to be around 2 amperes. Okay, and this ID we use to calculate what is this. Okay, so from this itself you can understand that the forward voltage drop is VD, that is this particular certain voltage, VD plus ID into RD. Okay. Okay. Any doubts over here? You can go ahead and ask. But yeah, it's pretty simple. You just need to plug in with the equivalent circuit of a diode. Okay. Yeah. So again, the same thing is given over here. First, calculate what is the current, and then use it to calculate what's the voltage. Okay. Okay. Same thing, but there is a huge difference over here. From the piece-wise model of a diode, we get dynamic resistance of diode as 50 milliohms. Okay, same thing. The voltage of 0.6 volts. Diode is connected in series with a 40 volt square wave voltage source. Fine till this point, but point is duty ratio of 0.5. Okay. Earlier they did not mention what is the duty ratio, so we assume that it's a constant voltage source. Okay. So previously also I drew it something like this, but since they did not mention what is the duty ratio, we can assume that it's a constant voltage source, okay, of 40 volts. They did not mention what is the duty ratio. However, in this particular problem, they are mentioning that the duty ratio is 0.5. Same problem, just the duty ratio is 0.5. So your voltage source is going to be something like this, okay. And if this is your switching period Ts, it's going to be Ts by 2, right? Why? Because duty ratio is 0.5. So for 50% of the time duration, we're going to have 40 volts. And for remaining 50%, you're going to have 0. So 40, 0, 40, 0, right? So that's how it's going to go. Okay. Same thing. And the question is on state power loss for the diode. Okay. So you need to compute what's the power loss, P loss. Okay. Right. So first we will write what all is known. That is VD 0.6, right? Then your RD is 50 milliohms, and your voltage source is 40 volts. However, it's a pulsed wave, right? It's going to be something like this. Okay, so this is your V, and your RL is 20 ohms. Right. So your RL is 20 ohms. Find out your P loss. First, remember one thing, that the equivalent representation of a diode in practical terms is going to be something like this. Okay. Wherein your this is VD and this is your RD, and it's a diode current. But there's a huge um, thing that we need to ensure over here. That is, if you want to find out the power loss, right? So that's what is asked in this question as well. Yeah. So just we will go back to basics. If you have a resistance and you pass a current, you pass a current. So what is the power loss? We call the power loss as I square R, right? But what is this I? Is it I RMS or I average? If you remember the basic definition of RMS current, you would understand that RMS current is that amount of current or the equivalent current which causes it to heat up, right? So this is the current that causes the power loss in the resistor, okay, and causes the heat to increase or temperature to increase, okay. So the power loss for this resistor is going to be I RMS square into RD, okay. However, for a voltage source, right, for a voltage source, if someone asks what's the power loss is going to be simply V into I average, right? V average into I average. Okay. So the power loss is going to be VD into I average. Okay. You need to compute what is the I average. You need to compute what is the I RMS. Sorry. You need to compute what is the I RMS and then find out the power loss. Power loss is basically VD into I average plus IRMS square into R, right? I'll just write it over here. We wrote this as something like this. So the power loss component is going to be VD, RD, and you have ID. So power loss component is going to be VD into I average plus RD into IRMS square. Okay. Fine. So this is the power loss. If you compute this, you get the answer. VD is given in the problem. RD is given in the problem. Just find out what is I average. Just find out what is IRMS. Right? And your answer is done. Now we will go back to the problem. It is given that it is in series with a 40-volt voltage source with a duty ratio of 0.5. Okay. So you have something like you have something you have something like this. Okay. And one thing is you need to find out what is ID average and ID RMS. Again, the same thing as the previous problem, just that over here, since nothing was given, we assume that there is only a single current ID of 2 amperes, right? Or exactly 1.965 amperes. In order to find out the average and the RMS values, we will go back to their definitions. Okay. So what is the definition of average? Average means it is 1 by t integral 0 to t f of t dt, right? That is, you simply find out the area. Okay. For RMS, it is basically 1 by t, right? Integral 0 to t a square of t dt. So it is, we have found out the mean square and it is actually root mean square, right? So this is your RMS, right? So what is the function that we have over here? This is the voltage. Okay. That is 40, 0, 40, 0. And what is the load we have? We have a resistive load. So the current will also follow this profile, right? That is ID 0, ID 0 and stuff. Were you able to get this point? Your voltage is a simple square wave. And since the load is a resistive load RL, the current will also follow a square wave profile, right? So how do you find out the average? ID average is simply the area over here divided by the time period, area by TS, right? So your ID average is going to be capital I, capital ID that we calculated into the duty cycle, right? Duty cycle is 0.5. Duty cycle is 0.5. Okay. And what is ID RMS? ID RMS will be ID into root over 0.5. Okay. Some of you may have doubt as to how I wrote directly 0.5 and how I wrote directly root over 0.5. I will come to that. But till this point, is it fine? We took the average and the RMS values. We just need to compute what is the average and the RMS values. Fine. So let us go to a basic square wave. Let's say this is your TS and this is some D times TS. It's a fraction. Sorry. Okay. Okay. So if you have a function something like this and it is having an amplitude of A and it is having an amplitude of 0, A, 0, A, 0, and so on. Right? So how do you find out the average? Average is basically area by time period. Okay. So what is the area? Area is this square over here, right? That is A into dTs divided by total TS, right? right? So basically the average is going to be the duty into A, right? A is the amplitude, A is the amplitude, right? And D is the duty. And what is the RMS? RMS is going to be, by definition, root mean square, right? So RMS is going to be 1 by Ts integral 0 to T f square dt, right? So root over 1 by Ts integral 0 to dTs amplitude square into dt. Okay. So if you do this, oh my god, why did it vanish? Just give me a second. Yeah. So RMS is 1 by Ts f square dt, right? So root over 1 by T integral 0 to dt a square dt, right? So what do you get? So you will be a is common, right? And it will be dt minus 0. So a into root d, right? So that is amplitude into root over d. Okay, root over duty. So you understand that for a square wave, average is, oh, okay. So average is, oh my god, why is it getting erased? Yeah. So averages averages amplitude into duty RMS. I don't know, there is some problem over here. Yeah. So averages amplitude into duty RMS is amplitude into root over duty. Okay. Yeah. So let me just fill this up. RMS is 1 by T, 0 to T, a square dt to dts a square dt. That is a into root d. Okay. Okay. So that is why I wrote ID average is ID into duty, that is 0.5, and ID RMS is ID into root over 0.5. Okay. So we'll just do the math over here. Yeah. So ID average is going to be 1.96. If I remember right, what is the value? 1.965 into 0.5, and ID RMS is 1.967 into root over 0.5. Okay. 0.983 amps, and ID RMS is Okay. So with this information, we can calculate what is the power loss, right? Power loss is VD into ID average plus IRMS square into RD. So P is equal to VD into I average plus RD into IRMS square. Okay. So VD is 0.6 into I average is 0.983 plus RD is 50 milliohms into IRMS is 1.389 whole square. So how much does it turn out to be? Yeah. So around 0.66 watts. Okay. Yeah. So this is what they have done as well. That is conduction losses I square R plus VD into ID average. So ID RMS is computed as I into root over D. I average is I into D. So ID average are computed, and finally the conduction loss is computed to be 0.685 watts. Okay. We got 0.66 watt. Yeah. It's almost same. Okay. Fine. Any doubts in this question? I took a pretty long time to cover actually due to some laptop issues perhaps. But yeah, I think you get the crux, right? Okay. So the reverse recovery time of a diode is 4 microseconds. What should be the peak reverse recovery current? Reverse current to recover the stored charge during the changeover from forward to reverse blocking conduction. Stored charge is 100 microcoulomb. Okay. So TRR, right? So the TRR is given as 4 microsecond and QRR is, excuse me, 100 microcoulomb. Okay. What should be the peak reverse recovery current? IRR peak should be how much? I guess you would have gone through the basics of reverse recovery. That is, you know that if the diode is conducting the forward direction, something like this, and if you turn off the diode current is going to fall something like this and then go to zero. Okay. This is your IRR and this is your TRR. Okay. And the stored charge over here or the area is going to be QRR. Okay. So the area is QRR. How do I tell? I into T is basically the charge, right? And that's the area over here. So this particular thing can be approximated as a triangle. Okay. So if I can approximate this as a triangle, I can write that the area or QRR or the area is going to be half into base into height, right? Half into IRR into TRR, right? So this is the area. From this relation, you can find out what is IRR, right? So QRR is given, TRR is given, therefore IRR will be 2QRR divided by TRR, right? So 2 into 100 divided by 4. Okay, micro and micro get cancelled eventually. So you get 50 amperes. 50 amperes. Okay, simple, right? We assume that this is a triangle. Okay, so the area is basically half into base into height, right? So I think this is a simple problem. 50 amperes, right? Yeah, same thing is being repeated over here. So we'll go on to the next question. An ultra-fast diode, RURG5060, some diode part number, carries forward current of 50 amperes. Okay, so IF is given with a DIF by dt of 100 amps per microsecond. Okay. From the data sheet, find out the peak reverse recovery current. Same thing, right? And it's even simpler because in the data sheet, the TA is given. That is, the time to reach the peak reverse current is given as 30 nanosecond, right? It's given in the data sheet. For a forward current of 50 amperes and df by dt of 100 amps per microsecond, it's given that typically the TRR is 30 nanosecond. Okay. TA is 30 nanosecond. Find out the reverse current. Okay. So this is what we are dealing with right now. So obviously your peak reverse current is going to be what? I is equal to di by dt into t. Okay. So excuse me. So di by dt is 100 amps per microsecond. That's given in the problem, and t is given as 30 nanosecond in the data sheet. Okay. So from this you can find out that your peak reverse current is going to be 3 amperes. Okay. Because micro and nano they are going to convert as 1 by 1000. So yeah, obviously it will be 3 amperes. Okay. So the peak reverse current is 3 amperes. Right. Okay. So any doubts so far? I'll just pause for a minute over here. If you have any doubts, please let me know. We have seen quite a few numerical problems in thermal aspect and then in power loss towards power loss, and we also saw problems on reverse recovery, right? So these are major questions that can be asked from diode portion. So any doubts so far, you can let me know. Hi Arjun, so you want me to repeat the last problem once again? The di by dt problem, or is it fine? The di by dt problem is just di by dt into t. That's it. So simple, right? Find out the peak reverse recovery current is the question. Let me see if I have turned on my camera. So the peak reverse recovery current is a question. So you know what is the DIDT, and um, they have given what is the total current as well. Don't get confused by this 50 amps of current. They have given just the di by dt, and from the data sheet you can find out what is the TA, right? From this portion, from this diagram, you can understand that during this TA, at the end of this TA interval, it's going to touch your peak reverse recovery current. Okay. So TA is given as 30 nanosecond, and you know what is the di by dt? So di by dt into t, right? It will give you what is I. right? Basically, it's just dimensions, right? So dA by dt into T. So 100 amps per microsecond into 30 nanosecond. It's mentioned over here, right? So the current is going to be 3 amps. Fine. Okay. Is it fine, Arjun? Yeah, thanks. Okay. So we will go ahead. Which of the following combinations of diodes allow the okay? So we still have only 5 problems, right? So which of the following combinations of diodes allow the flow of current from point A to point B? Okay. So this is so this is A, this is B, this is C, and this is D. Okay. So obviously you know that diode can conduct current from anode to cathode. Okay. Okay. So you just find out how current can flow between A to B. You can understand seeing this diagram that this diode and this diode are kind of an anti-series. Therefore, current cannot flow, right? Because from A there is no path at all. It cannot flow this way. It cannot flow this way. So it's not option A. And what about option B? Current can flow like this, yes. Then it can flow either through this or it can flow through this as well. So yeah, B is one of the correct answers. Okay. And what about option C? Current can flow through this diode. It cannot flow here. So current can flow like this, but it cannot flow here. It cannot flow here. So definitely not option C. And what about option D? Current cannot flow here. It can flow here. Yeah, straight path is available. So both option B and option D are fine. So I guess in your exam you have multiple choice questions wherein more than one option is correct. So please take care of that as well. Okay. So both B and D are correct over here. A diode is connected between a DC source VDC equal to 10 volts and load resistance is 10 ohm. The equivalent circuit is shown in figure with RD as 0.85 ohm and voltage drop is 1.1 volt. Calculate the power drop across the diode. So we have solved enough problems with this, I guess. But anyway, what is P? P is basically IRMS square into RD plus so P is basically IRMS square into RD plus I average into VD. Okay. So oh my god, why does it take this? Okay. So you know that P is IRMS square RD plus I average into VD. Okay. So your VD is given and your RD is given. Just find out what is your IRMS and I average and plug it over here. The good thing is they have told that it's a DC source. It's not some square wave that we saw earlier. So it's even simpler. It's just a DC source of 10 volts. So IRMS, I average, all of them are one and the same. Okay. So what is I? In this circuit, just apply KVL. I will be basically I will be VDC minus VD divided by RD plus RL. Okay. So 10 minus 1.1 divided by 0.85 plus 10. So what is the I that you get? 0.82. 0.8 amperes. Since it's a DC source, I RMS, I average, everything is one and the same. Okay. So just plug it in over here, 0.82 amps, right? So 0.82 square into RD plus 0.82 into VD. Okay. So around 1.474 watt. Okay. Simple question. Yeah. So it's 1.47 watt. Okay. We'll go ahead with the next question if you don't have any doubt. Calculate the forward voltage drop of the diode for the figure shown in question 21. So same question. What is the voltage drop? Okay. So from this figure itself, you can understand what is the voltage drop. Voltage drop will be I into R plus V. Right? Simple. You can understand, right? The equivalent diode representation, as you know, is going to be VD in series with a resistance VD and RD. So what is the voltage drop? VD plus I into RD, right? So VD is given as 1.1 plus I is what we calculated as 0.82 and RD is 0.85 ohms. Point 0.82 into 0.85. Okay. 0.82 into 0.85 plus, yeah, so 1.797 volt. So this is your forward voltage drop, right? Yeah, so 1.797 volts. Okay. Okay. Last two questions. Consider a current diode. Any doubts so far? Okay, so I'll just add a new slide. So, okay, so consider the current diode with the current ID flowing through it. Okay, if the characteristics of the diode and current are as shown, calculate the total conduction losses in the diode. Okay, so from this graph itself, you can understand that your VF, or I should not call it VF, it can be called as VD, right? Your VD or the cut-in voltage is 0.6 volt and your RD is 0.02 ohms. Okay, simple, right? Okay. And you have the diode current as something like this. This is something that we saw in an earlier problem as well. So you have 10 amps, 0, 10, 0, 10, 0. This is how the current is there. Find out the total conduction losses, that is P loss. Same problem we have solved earlier as well. Okay, just that we need information on what is IRMS and I average. Okay, so from this itself you can understand that your I RMS and I average are something like this. Capital I into D. Capital I into duty is your I average, and capital I into root over duty is your I RMS for a square wave. Right? It's not for a sine wave or something. Okay, you need to, you should not generalize it. Right? For sine wave, you should again find out what is the average and then um, proceed average and RMS. Okay. So for a square wave, I RMS is I into root D. I average is I into D. Okay. So 10 into, this is TS by 2, right? So it's a 50% duty cycle. Okay. So D is 0.5, right? So 10 into root 0.5, this is 10 into 0.5. So I average is 5 amperes and I RMS is 10 into root 0.5, right? So 10 by root 2. So 7.071 amps. Okay. So you have what is IRMS, you know what is I average. You just go ahead and calculate what is P loss. P loss is VD into I average plus IRMS square into RD. Right? So your VD is 0.6 volt. From the graph, you understand that VD is 0.6 into I average is 5 plus IRMS is 7.071 square into RD is 0.02. Okay, just compute what this is. Yes. Yeah, so around 4 watts. Okay. Yeah, so again, from the characteristic, you understood what is VF and R, and you can find out what is I average and I RMS. Okay, so total conduction losses can be determined, right, as 4 watts. Okay, so the last question for the day. Yeah. So refer to question 23 to determine the maximum safe ambient temperature for the safe operation of the diode if the junction to ambient thermal resistance is 30 degree per watt and the equation and the allowable junction is 150 degree. Okay. So EJ is 150. Okay. And R theta is 30 degree per watt. What should be TA? Okay. So that your TJ does not exceed 150 degree. Again, go back to the relation that TJ is TA plus P loss into R theta, right? So TJ is 150 is equal to TA plus P loss was 4 watts, if you remember in the previous question, into R theta is 30 degree per watt. So TA would be 13 to 4 is 120, so 150 minus 120 is 30 degrees. So, but over here, of course, the answer is A, but why should TA be less than 30 degree? It is asked that TJ should be at most 150 degrees. So TJ, it's an inequality that we are dealing with over here. So TJ should be less than or equal to 150 degree. Okay. So for TJ to be less than or equal to 150 degree, you can understand from this relation that this ambient should also be less than or equal to 30 degree, right? You want TJ to be less than or equal to 150. Therefore, TA should be less than or equal to 30 degree. Okay. That's why your TA should be less than or equal to 30 degrees. Okay. Got this? Yeah, same thing is given over here. Yeah. So thank you everyone for your attention. So actually I'm not keeping well, so I couldn't concentrate too much. But yeah, so any doubts so far? Arjun, you have any doubts? Sorry, I didn't see the chat in between. So yeah. If you have any doubts, you can let me know, or else we can close for the day. Yeah, thanks a lot. Okay, thanks everyone. Good night. Thanks for attending. I will close the session.
Thank you, sir.
Thank you.